bar 36, and this is to support the exploratory research in the area of space applications and satellites and spacecraft, and the work was in support of Thales Alenia Space and Airbus and ESA. So quickly, just for the application of these low CTE materials, well, they're stable with temperature, and they often are required in order to match the thermal expansion of some other material which they're joined to, so like carbon fiber materials and so on, and to give dimensional stability. Some of these space applications require the structure not to move as the temperature changes, and sometimes the cycle in the satellite can be plus or minus 60 degrees according to the orbit. In aluminium silicon X, you also get good thermal conductivity, which is often important for managing heat in spacecraft, and it has a much better thermal conductivity than titanium, which is currently used as a low CTE material, and it also obviously has a low density. So first, talking about the laser beam melting of the aluminium silicon X, it's important for electronic packaging, thermal management, and so on, and reducing stress. Aluminium alloys generally have high thermal expansion. It's typically 23 times 10 to the minus 6 per Kelvin. And using a low CTE filler like silicon, which only has an expansion of 2.6, almost a tenth, means that we can generate a material with a lower CTE. These materials are produced, but they have to be produced by fairly advanced and fancy techniques, so powder metallurgy and spray forming, which tends to mean you get an ingot of material which then has to be processed into a shape just by EDM processing, and fairly simple structures are generated that way. So to talk about the work we did, we started with two different base alloys. One was aluminium 6061, which is quite a high strength alloy, and was the first selection in order to produce a very good material. And then we also used the standard aluminium silicon 10 material, because that turned out to be quite a lot easier to process. So the materials we had were gas atomized by TLS in Germany. We had them pre-alloyed, some aluminium 6061 with 25% weight silicon. So that material was pre-alloyed. Then we had our standard aluminium silicon 10, which is produced by them, and then they produced some silicon, which was initially in the 45 to 100 micron range, but then we sieved that to 50 microns. So we almost had mono-sized silicon that we were using in the project. And you can see the median size of the powders was typical for laser beam processing in the 30 to 45. The powders were obviously analyzed for chemistry and so on, and we looked at the morphology, and you can see all the powders are nice spherical materials, which made them very suitable for the processing, and they were blended in the case of the aluminium silicon with extra silicon. And we did a series of trials on our concept machine. So all the work was done at 30 micron layer thickness, the scan spacing 120 microns, and using the island scan, which comes with the standard processing on a concept machine. So these are 5 millimeter squares, shift 1 millimeter and rotate by 45 degrees on each layer, obviously processing in argon atmosphere. And we did a series of trials investigating the ranges of the processing power and scan speed. So initially with the pre-alloyed material, and then with the aluminium silicon with 15% silicon added, and then with 40% silicon added in. So this is just one of the examples of the sort of properties we can measure. So you can see as the lower power, then you are getting full density. So it's only 125 watts at quite a high speed, and the density of that is only about 70%. But as the properties are increased, then you can get towards full density. So as the power was increased, this is 225 watts power, and the speed was slower, then we were able to get to full dense parts. Obviously you can overdo that, and if you went to too much power, with too slow a sand speed, then you start to get some key holding porosity and some gas pools produced. So from that we were able to select the best conditions, which were 325 and 1500 liters per second. And then that was somewhat modified for some of the alloys because the other problem you get with the samples that they would start to crack. So at the lower energy conditions, we're finding quite bad cracking. But as you increase decrease the scan speed and increase the laser power, then that will be overcome. So it was better to run the conditions with quite high energy towards the place where you're starting to get some gas porosity in order to avoid the cracking. This is in the 6061 material, which was more difficult to process. And in the end, we had a process map, and you can see this is here. So all this area in the green was processing conditions where we could get high density, so above 99%, but only in this corner would we get crack-free samples. This is in the pre-alloyed material. The other material, where we're mixing the standard alloy silicon 10 with a further 15% weight of silicon, we find that the crack-free zone is a lot larger and is a lot easier to process. As you might expect, the structure is much finer than you get in a cast material. This is a chill cast aluminium silicon with 40 silicon in, and this is our material with 40% silicon added in to the same material. Actually, this is a 50 weight material, so this is also 50 weight percent silicon, when you add these together. So this is a much finer structure. So we wanted to investigate, have a quick look at the thermal expansion coefficient for the materials and also look at the mechanical testing. We only made a very few samples for each one, so we just had these very small samples produced on the machine just by EDMing a small block. And we had these standard CTE samples produced as well on the machine for each of the materials. And this is the CTE results for the different materials. This is the CTE for the base material. So for the 6061 and the aluminium silicon, then they're both above 20. But when you add the silicon in, then it brings it right down. So this is just the wall of mixtures estimate of where it would be. And these are the actual measurements. You can see they're all in agreement with that. And increasing the silicon content, this is with 40% silicon, has brought the thermal expansion by 10 to 14. That's very interesting, and this compares with the standard sandite material, which is produced by spray forming, and you can see you get very similar expansion coefficients for these materials. So this is quite a nice alternative way to produce these sort of materials. And it would be interesting to go and add more silicon still and carry on further down so that we could even produce materials with even lower expansion coefficients. Tensile testing was only 3 samples, and a couple of them aren't very good, but you can see the middle ones have quite promising conditions, and this suggests we need to probably develop the processing a little bit more. Which is still in the fracture structure. We can see some silicon particles in there, so we probably need to improve the alloying of these materials just a little bit more to make sure that we've got the silicon properly melted in the material. But this is quite a high figure for the yield strength of this material, so it shows some promise. So basically, we investigated 3 high silicon alloys. We achieved high density for all the materials. We get some keyhole porosity if we go over in terms of energy density. And we generally found that the aluminium silicon 10 with the added silicon was a lot less crack susceptible than the pre-alloyed material. Get very fine microstructure, and we get effective alloying. So on the whole, we avoid the inherited big silicon particles that we've added in, and those have dissolved. And we have the potential of producing enhanced mechanical properties, but that certainly needs some more development. And we generally have lowered the CTE values through adding the silicon. So it needs a little bit more development on these materials, but I think they have a lot of potential and will allow the generation of quite complex structures and so on in these materials in the future. So the second part of my talk is about processing of INVAR 36. This is a material with a very low CTE. It only happens at the 36% nickel. So there's a big change in the coefficient of thermal expansion as the alloy hits 36%. So we had the material produced by TLS again. See, the powder is quite nice, between 25 and 50 microns, and very spherical. There was a few iron-rich spots within the powder in some of the larger particles, but they didn't cause any problem. And again, we went through a case of optimizing the processing conditions. This is all processing at 400 watts, and then we're just doing some small trials at different scan speeds to see where we get the high-density parts. So you can see that if you don't have enough, rather if you're scanning at too high a speed, then you get lack of fusion defects. But as you slow down and increase the energy density, then you can get to very high density parts. And the material has a very wide processing window. So again, we produced some samples and measured the CTE of the material. And this value that you get is about 1.4, which is a good match with that's expected in the literature for this material. So this is what the material is used for. It's used for cases where the thermal expansion coefficient needs to be very low, and processing by SLM gives you that option to do that. We measured the mechanical properties. There are some targets which we were set by Thales here, down at the bottom, and the material exceeded those by a long way for the yield strength and UTS, just about for the elongation and certainly for the CTE. So they were exceeded for that. So the processing of the material seems, quite suited to this. And there was a publication which you may want to look at, which is also in your brochure, which we wrote a paper in Actimet. So then that work was then taken on. So we were doing this preliminary work just at Birmingham, but it was taken on by the rest of the group who was interested in these INVAR material. And we produced these different components, which were there for, this is the part for Airbus, which is downstairs in the cabinet. And you can see that component. And some other parts for Thales, which they were interested in. So it shows the possibilities of processing with this material. And these parts actually went into a satellite component. So that will be covered in more detail by Nick Lavery this afternoon in his presentation, which is in this afternoon's talk. And he'll carry on talking about how that was further developed by the group and the parts that were produced. So the conclusion is that we can use laser beam melting for these low CT materials, and we've demonstrated it both for aluminium silicon and for the INVAR. The processing conditions can be just optimized in the normal way as you do for laser beam by adjusting the speed and power. And we can produce fully dense, crack-free microstructures in these materials, allowing, in the end, some demonstrated parts to be made. Okay, so I think this shows we have the potential for using this for producing lower weight components and redesigning parts. The part that we made for Airbus is just their standard component, but I'm sure it could be redesigned and lightweighted and the normal things that you get using additive manufacturing. I must thank Teresa and Luke at Birmingham for the aluminium silicon work, and Chung Lee and Luke for the INVAR 36 work. And then we had a big partnership in the APOD, which Nick's going to talk about this afternoon. Okay, can I answer any questions? Hello.
Just a quick one on the aluminium silicon. Was that mechanically alloyed, or was it melted? The silicon added into the melt and then atomized?
So the silicon was put into the melt for the 6061 material. So it's a proper melt, and it's atomized, and then they took out the fraction that we needed from that. For the other stuff we made by blending. So we took the normal standard aluminium silicon 10 material, which we process a lot of, and it was just blended with the silicon either at 15% extra or 40% extra for the two different trials. Pure silicon powder blended in, that's right, yeah.
Which is why you were seeing on one of those pictures maybe a silicon.
Yeah. So getting all of the silicon to melt within the melt pools is what needs to be done there in order particularly to improve the elongation and tensile properties. I think so. I think it'd be really nice next step, yeah. Like it was mentioned earlier, but it's very expensive to get special batches made up, but you can do this sort of blending work and you can show some promise for these materials, and then you can go the next step and say, yeah, let's get that atomized and process it from there. So I think that would be obviously the next stage for this. And to go past 40 weight % as an addition. And a lot of the interest in this, the aluminium silicon material would be at almost 70% silicon. You know, that's where the thermal expansion starts to match the carbon materials and things. So, yeah. But there's a lot of, you imagine at the moment that Invar is used in satellites, you know, although it's a density of 8, this has a great potential for bringing that down and being more useful.